I'm sorry, really, the electricity went out and suddenly the internet disconnected. So, I mean, it's the first time a blackout has happened here in the UAE, so I honestly don't know. There's no problem, Dr. Islam, so I apologize. I don't know where I stopped because I was talking a bit absent-mindedly and didn't really pay attention. I mean, we were discussing the intensity of the inflammation with the linear attenuation coefficient and the relationship between them, right? Well, naturally, as you might expect, the thicker or more substantial in thickness my material is, meaning if x1 is different or smaller than x2, then in this context, if x1 is less than x2, the attenuation increases with thickness, right? The amount of attenuation or the attenuation coefficient, or indeed the amount of attenuation that will actually occur from the radiation will increase. The attenuation coefficient does not express the attenuation itself. It expresses a specific property of the material. For example, if I take 1 centimeter of lead and 1 centimeter of wood or aluminum, which one has a higher attenuation? They have the same thickness, but which one will cause higher attenuation for X-rays? It will be lead because its density is higher and its atomic number is higher. Its properties allow it to cause higher attenuation. Now, if I want to reduce the intensity of radiation to half, what do you think the required thickness will be at that time between the two brackets, which is the half value layer of lead? Is there anyone who wants to speak? Okay, again. If you want to reduce the incident intensity of radiation to half and you have lead and aluminum, then the required thickness that will reduce the intensity of radiation to half is called the half value layer. In order to achieve this, it is important to understand that the material used plays a crucial role. Now, will the thickness of lead be less or greater than the thickness of aluminum? Therefore, considering the properties of each material, one can determine the appropriate thickness required. What will the thickness of lead be? It will be less, right? I said the required thickness, which is the half value layer for lead, is less because its attenuation coefficient is high. The relationship between the attenuation coefficient and the half value layer is an inverse relationship. However, when I talk about the half value layer, the first thing that comes to your mind is thickness. So you might think of a direct relationship. Yes, the relationship I am talking about is that, as a general rule, the thicker the material, the greater the attenuation. So there is no problem there. But when I talk about the half value layer, I mean the required thickness that reduces the intensity of radiation to half. The half value layer in relation to the attenuation coefficient of my material means that the greater the required thickness to reduce the attenuation coefficient to half, the lower it becomes. That's why they say the half value layer for lead is equal to the half value layer for aluminum. Of course not. It will be less because the attenuation coefficient of lead is higher than that of aluminum. Why will the thickness of lead be less? Because the attenuation coefficient of lead is higher than that of aluminum. All right, this is the idea of the half value layer and its relationship with the attenuation coefficient. I will link it to you in the equation. If you want to calculate the half value layer, it is 0.693 divided by the attenuation coefficient. This means that with the knowledge of the attenuation coefficient, you can calculate the half value layer or the required thickness to reduce the intensity of radiation to half for any material based on its attenuation coefficient. All right, you can calculate the half value layer or the required thickness to reduce the intensity of radiation to half for any material using its attenuation coefficient. If we are talking about thickness, then your statement is correct. As thickness increases, attenuation decreases, and as attenuation increases, that's fine. You are discussing the required thickness of the half value layer and its relationship with the attenuation coefficient of the specific material. We must differentiate between attenuation and the attenuation coefficient, which is an indicator of the material's ability to attenuate radiation. I hope this part is clear. I was saying that in a monoenergetic beam, the first half value layer equals the second half value layer, which equals the third half value layer. There is no problem. Now, if you have a polyenergetic beam, like an X-ray beam, ranging from 10 to 100 kilo-electron volts, all incident on the first half value layer, or a certain thickness, for example, what will happen? I have a range of energies. I don't have a large energy, meaning not all of them have a single energy. The half value layer here, or the thickness of the material, will act like a filter, removing all the low energies of X-ray photons. All the X-ray photons that can cause attenuation will be removed from my beam. Let's say the average energy here is from 10 to 100, for example, 50 kV. What does that mean? It means the average energy for this range of energies is 50 kV. Now, the average energy of our air is normal air at 50 kilo-electron volts. The thickness here can reduce from approximately 10 to about 20 kiloliters, while it can range from around 30 to nearly a full 100 kiloliters. The mean energy level, which was initially at a value of about 50 units of measurement in terms of kiloliters, has escalated significantly up to 65 kiloliters, because the average derived from 30% is different compared with what you get when averaging 10%. This escalation in average energy means that your mean energy has increased overall, which is referred commonly as beam hardening phenomenon. Beam hardening essentially means that you have effectively increased and enhanced the mean energetic level of your beam through utilizing an appropriate filter, or alternatively applying proper material thickness designed specifically for absorbing softer radiation types, while allowing high energy X-ray photons passage through unimpeded. Now then, if I want precisely determine what constitutes half value layer or specific thickness, required reducing intensity starting at 65 kV down exactly halfway point. Under these circumstances, will second half value layer's necessary thickness be greater than equal to less first one? It will indeed be greater. It will be larger because your mean energy has increased. We discussed that the intensity number multiplied by the energy of photons. So since your mean energy has increased, you will need a greater thickness of the same material that I call the second half value layer to reduce the intensity of radiation to half. That's why if someone asks you, what about the second half value layer for the polyenergetic X-ray beam? It will be larger, they might ask you, and you might mess it up. For a poor energetic X-ray beam, it will be greater than the first half value layer, not less or equal. Of course it will be greater, because your mean energy has increased and so on. This is clear, doctors. So, we talked about the relationship or the difference between the half value layer, in the case of a polyenergetic X-ray beam, and the difference between the first half value layer and the second half value layer, as well as the relationship of the half value layer with the attenuation coefficient. We also discussed the difference between thickness and attenuation, or thickness and the half value layer. The half value layer decreases as the material's density increases. If the X-ray beam energy increases from 100 kV to 120 kV, consider the radiation's photon energy. Instead of working on what you are currently working on, you will need to increase the energy. So you need to. It should have a greater thickness in order to allow for air attenuation. This is normal. If the air is reduced, the thickness of the air from the same materials will also decrease. If your internet is lower, the half value layer from the same material will decrease in order to reduce your internet for it to work properly. In shielding calculations and the related calculations, it is often stated that, for example, one should use the value for the 10th, which is always used. Using the intensity of radiation for the 10th value of incident radiation, this value is always used. He told you that, to be a bit realistic, the topic of the attenuation coefficient is represented by something called the معامل التوهين الكتلي. This means you need to include another factor related to the material itself, which is the كثافة المادة. So, if you divide the معامل التوهين الخطي by the كثافة المادة, regarding the density of the material, it gives you something called the معامل التوهين الكتلي, which is considered its unit, measured in grams per square centimeter. The mass attenuation coefficient is considered a characteristic of the material. Sometimes the mass attenuation coefficient is used, and other times the linear attenuation coefficient is used. This is not the main topic, and you don't need to focus too much on it, but you should know that it is a relationship between the linear attenuation coefficient divided by the density of the whole material. These are the factors that can affect the concept of attenuation. If the beam energy increases, the attenuation will reduce the ability of the material to attenuate. The percentage of transmitted photons will increase. If the beam energy increases, you will need a high half-value layer to reduce the intensity of radiation. If your intensity has increased, then you need a high value to reduce it. The طاقة الشعاع determines the dominant interaction type. At low energy, the أثر الكهروضوئية is dominant, and the transmitted photons are fewer because most of them become photoelectrons. As energy increases, تشتت كومبتون dominates, and the أثر الكهروضوئية is less significant, resulting in a higher number of transmitted photons. Most interactions are تشتت كومبتون. Regarding the atomic number, if the atomic number of the material increases, will this increase the attenuation? Of course, it will increase the attenuation, because an increase in the number of atoms or an increase in the atomic number means what? It means that you have an increase in the number of protons and an increase in the number of electrons, which leads to an increase in the probability of interactions occurring. So, this results in an increase in your attenuation. This is something we always observe, for instance, in lead materials, which is why you will find that its atomic number is higher than that of aluminum or other materials. Now, the point that Dr. Hani mentioned about density and electron density, there is a difference between density and something called electron density. Let me clarify this for you. If I take, as an example, a material like lead and a material like cotton. The cotton, for example, and the same thickness of 1 centimeter and 1 centimeter, do you expect that in 1 centimeter of lead and 1 centimeter of cotton or other different materials? The L or way takes the same dimension as you. Is that clear? Okay. Are you expecting it to be in centimeters? And the 1 centimeter of cotton or water or any other different materials, do you expect that? The number, oh, it seems like here is the same as there. You are using the same thickness of 1 centimeter, right? Do you expect that the number of all atoms present in this thickness is the same as the number of atoms present in that thickness, even though you are taking the same thickness? Is there a difference or not? It will differ just a little bit. It will differ. All right. So which one of them is more? You have taken a centimeter. It means you are working as if you are working with volume dimensions. You took a volume of cotton or a volume of water, specifically 1 C-3 of water. Now, which one has more atoms? So if the number of atoms increases, will the ratio of electrons present increase or decrease? If you come to the conclusion that the lead you have took a cubic centimeter of it and took a cubic centimeter of cotton, the same volume, but not the same weight. Is that correct? I mean, if you take a cubic centimeter of, let's say, iron and cotton, which one will take up more space? God bless you. Even though both have the same weight, right? This is what I want to convey to you. Both have the same weight, but the volume is different, right? So why is the volume different? Because here, the cotton is lighter. Why? Yes, the number of atoms present in its cubic centimeter is less in volume. It has a smaller volume. When I talk about the number of atoms in a cubic centimeter, I'm not measuring weights. I'm measuring volume. So, you come to a certain material and take 1 centimeter in 3 dimensions or 4 dimensions. For example, you divide it and take a piece like a cake. You divide it and it doesn't matter what its weight is. You take a piece of iron and the same area with the same dimensions from cotton. Okay? So the number of atoms present, indicating the number of electrons present in a cubic centimeter. When I say that, when I compare the weight of muscle to that of water, it's clear, right? They say that when you take a cubic centimeter of muscle and a cubic centimeter of water, you will find that the two do not weigh the same, even though their volumes are equal. There is a difference between volume and weight. Their dimensions are the same. For example, consider 1 kilogram of cotton and 1 kilogram of iron. The kilogram of cotton occupies a much larger space. Now, if you take a cube from that kilogram of cotton, you will find out how many atoms it contains. While if you take the same volume from iron, what do you have? The number of atoms is high due to its high density. This means that the number of electrons is also high in that weight per cubic centimeter, which I call the electron density. The electron density present in the bone is significantly higher than that in water, which allows the bone to exhibit photoelectric interaction considerably more than water. This means that the photon effectively enables the bone to successfully perform photoelectric interaction significantly more than water. Now, when you discuss in detail about weight, if you take 1 gram of water and 1 gram of water, and you want to thoroughly examine the number of electrons present in that gram, you will find that the ratio is naturally present in the bone less than the ratio found in the water. It is less than that. Well, this story proves to me that I am in front of you. Well, the story is just indirectly indicating that I have you if I have your presence. Your atomic number is high, which means your atomic density is high, meaning the number of atoms has increased. The number of electrons per cubic centimeter has also increased, and this is what is present in the photoelectric effect. Note that the bone itself also experiences Compton scattering. It does not mean it doesn't happen. If you look at the curves we explained in the initial lectures, you will find that Compton scattering also occurs in the bone. Compton scattering also depends on the number of electrons present. It does not solely depend on that. However, as I mentioned, or as I was explaining, I have in the bone a higher number of electrons per cubic centimeter compared to water. So you will find that Compton scattering which also depends on the number of electrons per cubic centimeter, known as electron density, is higher in the bone. At the same time, it has a high atomic number and a higher number of atoms, which means it has a higher number of electrons. Therefore, the photoelectric interaction and Compton scattering are both greater in comparison to water. You will find that the percentage of photoelectric interaction occurring in water is lower compared to tissue. And the same idea applies to Compton interaction, which is also lower in water compared to tissue. You will find it consistent when you talk about water or soft tissue. It will be stable, whether you are discussing low energy or high energy. Right, Dr. Hani? Or did I confuse you?
What corresponds with Z power 3 means that the photoelectric effect has a direct relationship with Z power 3 and an inverse relationship with photointernet.
This is clear, but the idea is that the bone experiences Compton and photoelectric effects. This happens, and it is not possible. If you go back to the last lecture, you will find that there is Compton occurring in the bone, but this does not happen. However, the bone is less than the photoelectric effect, yes, but at the same time, it is higher than the bone. Do you understand my point? It means both interactions occur. You cannot say one is dominant over the other in the bone. Why is it dominant in the bone? Because, as you said, there is material and there are electrons that absorb. Excuse me, Dr. Hani, please. Because it is in the slide before the previous one.
It is written in the density that it depends on the number of electrons, and the electrons per gram depend on the number of neutrons. I mean, the number of electrons is correct.
This is written incorrectly. It has no relation to the topic. I mean, this is a number and a flick, and it's written incorrectly. Excuse me, sir. Both of them represent the number of electrons, but as I mentioned, one deals with mass and the other deals with cubic centimeters. For example, when you come to consider the number of electrons present in a certain material, it can be per cubic centimeter or per gram. If you increase the density of any material, you are increasing what? You are increasing the density, which is a property inherent to the material itself. It depends on the mass of the material and reducing the volume. So when I say that the density of lead is higher than the density of water, what does that mean? It means that you can achieve a high mass with a small volume, right? Or am I wrong? The water has a lower density, so you need a larger volume to achieve the same density that you would compare to. When you reach the same thing, the density relates to the mass of the material itself, and the number of electrons both have a relationship with the number of electrons, Dr. Hani. Both have a relationship with the number of electrons. The electron density. Doctor, when you talk about density and atomic number, an increase in density means, as you know, an increase in the photoelectric effect. To clarify what we were discussing to avoid confusion, indeed, an increase in density or an increase in atomic number means you have essentially increased the chance of occurrence. So the electron density, or the electron density that I was talking about earlier, is more related to computing scattering. It is what controls the computing scattering in different materials, more than the Compton scattering. In fact, it is what governs the basis of it. You will find that it is present, for example, in bone more than in water. The Compton effect occurs more in bone compared to water, just to clarify. I always say that the photoelectric effect occurs in bone. It happens at a higher rate when you compare it to Compton scattering. When you compare the photoelectric effect to Compton scattering in bone, you will find that the photoelectric effect is higher because bone has a high atomic number, and the same applies to the electron density. This might be a bit unclear, so if you need more details, I can create a video after the lecture and send it to you if you want a more detailed explanation. Now, there is something called off-focus radiation. I know that the topic of electron density is a bit complex, but let's proceed. Off-focus radiation occurs when some of the electron beam interacts with the anode only outside the boundaries of the focal area. This interaction produces X-rays, which I refer to as off-focus X-rays. The result of off-focus X-rays is that there can be interactions between the electron beam that is coming from the filaments outside the actual focal area or from the electrons, leading to the appearance of X-rays called off-focus X-rays. This can, of course, increase the patient dose or the skin dose during scanning, especially if there is no absorption by the X-ray tube material or the filters present. Of course, you all know about the topic of ice cream, the film radiography, the subject of imaging, and the topic of X-ray imaging or the imaging process. As we were discussing a little while ago about the process of developing an acids and the use of developer and fixer, this topic has become impractical for me now. It has become, as I would say, old-fashioned. The idea of using it has many problems, and the chemicals used and all that. However, we want to understand the concept itself in the imaging process. I have an incident beam of X-ray and a patient, and there is an interaction between the incident radiation on the patient with the interactions that occur, resulting in a transmitted beam of radiation. I need to receive this transmitted beam of radiation on a receptor, on an image receptor, on film. If I take the film material itself and expose it to light, what happens to it? I mean, if I take the film itself and expose it to light, I need a very high dose compared to the techniques currently used to produce the same image that I get using the film alone.